What's up, everybody? We're going to go ahead and go over chapter 27, this is homework number 5. This is all about resistor circuits. We're going to cover purely resistive circuits, and then we're also going to cover RC circuits, where we take resistors and capacitors and plug them into each other. So let's go ahead and just jump right into our first problem. And it's a good problem to start off with because this is just like a purely resistive circuit, and we're going to see, how resistors are similar and different from capacitors. Now, the long story short is that resistors function the same way as capacitors do with voltage. So in this first problem, we actually have a circuit that looks some, these are the two sides of the circuit. And there's going to be one side where we just have resistor 4 is the name of that one. And then there is another side of the circuit where we have resistors 1, 2, and 3. Call those 1, 2, and 3. And yeah, so these are two different sides of a parallel circuit. What that means is that the voltage over 1, 2, and 3 will all add together, and altogether it will be equal to the voltage drop over 4, because we could either go this way through our circuit, and we should get the same voltage drop as traveling this way through our circuit as well. So what that means is what I just said, but just to write that down again, is that voltage 1 plus the voltage 2 plus voltage 3 is equal to voltage 4. And we have some values here associated with these different graphs. So for one, voltage 4 is tied into the graph on the bottom, which tells us that we start with voltage A and we drop to 0. What that just means is that the voltage drop over resistor 4 is equal to voltage A. So we can go ahead and write that there. And what else? We have voltage B that we drop over resistor 1. So we have voltage B, and then voltage C is dropped over resistor 2. And then I do not know the voltage that is dropped over 3. However, since I have all of these other 3 values here, I can go ahead and solve for the voltage dropped over resistor 3. Now, ultimately, I'm asked to find the resistance of resistor 1 and 2. And in order to do that, I'm going to have to find something to do with either well, I have the voltages already, right? Because those values are given. These are like the delta VB and delta VC. So I already have those values. What I need to do then is relate those voltages back to the resistances. So in each case, this is going to be my equation. V is equal to I times R. So I know my voltage drops, and I know I'm solving for the resistances. I do not know the current. So where's my current going to come through? Well, this is our other rule. So we know that the voltage has to be the same on both sides of a parallel. That's what we use to set up our first equation here. But the other rule that we want to use is that the current is going to be the same through anything that is connected in series. So 1, 2, and 3 are all in series, which means they have the same current. Why is that useful to us? Well, we're able to find voltage 3 from this equation, as I mentioned, and then they give us the resistance of resistor 3. So the voltage 3 is going to be equal to the current times resistance 3. And now that I can find my current through resistor 3, since resistor 3 is connected in series to 1 and 2, that's got to be the same current through 1 and 2. So then I just need to relate the voltages that are dropped over each to the current that I'll solve for right here. And I'll get, for example, that the voltage over 1, which is equal to delta VB, will be equal to whatever that current is times resistance 1. And then similarly for resistor 2, I'll have voltage 2 is equal to delta VC, which is equal to that same current times resistor 2. Okay, so again, what are my rules here? If I have a parallel connection, such as the combo of 1, 2, and 3 being connected in parallel to 4, then the two sides of the parallel circuit will share the same voltage. And whenever I have series connection, everything that's connected in series, like here 1, 2, and 3, will all have the same current. Resistor 4, I don't know the current or I don't know necessarily a relationship between resistor 4 and the current through 1, 2, and 3, at least not yet. But I think, am I going to start using that? Not quite yet. We go one more problem. We will come back and get a rule to relate the currents through a parallel split right here. This is called a junction. But for now, let's do one more problem. This is problem number 2. Problem number 2 is a little bit of a strange setup because we have a variable resistor, which isn't a very like common or fundamental idea. But we also have internal resistance inside of these batteries. So here's our circuit. We actually have 2 batteries, and each battery is going to have an internal resistance, and we are ultimately solving for those internal resistances. So I'm gonna draw the internal resistance connected to each of these batteries. It's not in your diagram, but I'm gonna go ahead and add. So here's like one battery. I'm gonna go ahead and put a little resistor here, okay? And then we have our other battery down here, and I'm gonna put its little internal resistor as well. And so these are gonna be identical, and they're connected to this external resistor on the other side. And both batteries are going to have the same electromotive force. That's the EMF or the epsilon. And we're given that our external resistor is variable, but we do call it big R. Go ahead and label that big R. And yeah, I have to read this graph. Okay, we'll come back to the graph in just a second. But what I just want to mention is I think that we have identical. Oh no, we don't have identical internal resistances because we have 2 different graphs for the 2 different batteries. Okay, so it doesn't really matter which one is battery 1 and which one is battery 2. So let's go ahead and call this 1 and 2. And for internal resistance, I'm going to use little r1 and little r2. What is an internal resistance of a battery? Well, a battery is made out of metal. So inherently, a battery can be resistive. If you have an ideal battery, then in that case, you're saying that the resistance of the battery itself is 0. So oftentimes, you'll have an internal resistance of 0. You'll have an idealized battery. In this problem, though, we are taking into account the internal resistance of the batteries. Okay, now, because the terminals are lined up positive to negative, oops, negative to positive to negative. In other words, since they're connected in the the proper order, we know the voltages are going to add together, and we know that our current is going to flow around the circuit like this. And so what we can do here is something called a loop rule, and the loop rule tells us that we can how do I summarize the loop rule? I guess you just go around in a single loop from start to finish. So say start at this point down here, travel a loop and add up all of the voltages, and the voltages should all add up to 0. So the loop rule tells us that the sum of the voltages around a loop is going to be equal to 0. Why would our voltages be equal to 0 and not add up to some number? Shouldn't everything be like adding a voltage? Well, keep in mind, to go back to that last problem, we drop voltage over a resistor. In other words, a resistor uses up voltage, whereas a battery is going to add voltage to a circuit. So let's go ahead and take a look how this would work. We'll start at this point and we'll go up. As we move up, we go over our first battery, and our first battery is going to have our electromotive force, and we called it battery 2. So let's just say it's the electromotive force 2. This is the voltage. And then we also have the internal resistor. Now, this EMF 2 is a positive voltage because that battery is adding voltage. When we go from the negative terminal to the positive terminal, we are adding voltage. So we have a positive EMF 2. Whoops, I still wanted that. Let's do it here. Nope. Okay, positive EMF 2, but then the internal resistance of the battery, this R2, is going to subtract voltage out. So total, we have epsilon 2 minus whatever our current is times little r2. Then we keep traveling through our circuit, and we go over battery 1, where again, we're going to add in EMF 1 and then subtract out the internal resistance voltage. So we do plus epsilon 1 minus I R1. And then we continue traveling around the circuit until we go over the external resistor big R. And there we will have again, the resistor is going to use voltage. So we'll subtract I times big R. And altogether, this has to be equal to 0. Okay. So this gives us kind of a big, long equation. Now, we know a few of these values. So for starters, we know that the 2 epsilons are the same. In my problem, it's 2 volts. Yours will be different. And we will have different internal resistances. So those little R2 and little R1, we don't know. But we can read big R off of the graph. And specifically, when we read big R off of the graph, we will see, we can, pick specific points that are going to correspond to known values. So for one, we, sorry, getting a bunch of Slack messages. The worst time to get Slack messages. So the value that I pick off is where that graph for 2 crosses over the resistance axis. And at that point, of course, you'd have a total voltage for battery 2 that is equal to 0. So at the R value, where big R is equal to, it looks like it's R sub S on 2, we know that this entire thing here will be equal to 0. So this is 0. Oops. For big R is equal to R sub S on 2. And that lets us also read the value off for this whole piece right here. So just looking at the graph, we see that the line for voltage source 1 is going to cross over sort of a corner there. It looks like it's 4 lines up from the horizontal axis. So it would be 4/5 of whatever value is labeled on your horizontal axis, which for me is 0.9. So it'd be 0.9 times 4/5. And that would be this value. So 4/5 of 0.9. And thus that allows us to, replace this guy with 0, this guy with some actual value, and then we're going to replace big R with this value, R sub S on 2, and that will allow us to solve for a current. Once I solve for a current, then I can go back to the set of equations that I've essentially generated here. And so again, plugging all that stuff in, we're going to get some value for our current. And then we just go back to these 2 equations that we've kind of de facto set up. So we know that this first equation right here is essentially saying epsilon 2 minus I R2 is equal to 0. And of course, we know epsilon 2 is just the constant EMF given. So that will allow us to solve for R2. And then the other equation that we have is this one right here, which is epsilon 1 minus I R1 is equal to, in my case, 4/5 times 0.9. So in both these equations, you plug in the current that you find from doing the substitutions we discussed just a second ago. You plug in that current for I in each of these equations, and that will allow you to solve for the internal resistances. Okay, so this problem is kind of complicated and complex. The reason is because we have a variable resistor and because we're reading a graph. So I just want to emphasize this is a little bit of an advanced problem, and we're unfortunately doing it second in the homework. So if you're having a little bit of trouble, you're getting caught up, it's probably because of the part where we're reading that graph. But the most important thing is that we're going to carry forward is this loop rule and how we set this up. So again, you sum your voltages in a loop and it's going to be equal to 0. You gain voltage going over a battery from negative to positive, and you subtract off voltage going with the current through a resistor. That's going to be the most important thing that we did in this problem. The internal resistance stuff is a little bit less important. Okay, so let's go ahead and move on to our next problem, which is problem number 3. And in problem number 3, first thing they say right out the bat is we have ideal batteries. So remember, an ideal battery means we don't have to worry about internal resistance. And most of the time, we're not going to be worrying about internal resistance. So that's a weird problem that we just did, that was number 2, but it just has to do with the order that they are in the book. But here we have ideal batteries, and we're given their voltages as EMFs, which is, again, electromotive force, just another way of saying voltage. And we're given our resistances. They're all going to be the same. And we are asked to find 3 different currents. Okay, so in this problem, we have 2 batteries again. unlike the last problem where the batteries were connected terminal to terminal, and we could essentially just add their voltages together, here the batteries are on opposite branches of the circuit. So what does that mean as I'm attacking this problem? Well, I have one battery on this side with a resistor here. I have another battery on the other side with a resistor up here. And then there's a third resistor going right down the middle. And these all have different names. So this one is epsilon1, this one is epsilon2, and we have R1, R2, R3. And ordinarily from here, we could proceed using our loop rule to generate a series of equations just by doing loops around this problem. Now, they also, nicely enough, gave us the directions for some currents. These are kind of assumed directions, which are in fact going to be correct for this problem. But you'll notice that they give us this one right here. They say that this is I1. And they give us this direction over here. They say that this is I2. And then the last one they tell us is that I3 goes straight down. So we're going to do the loop rule in just a second, but the first thing I want to point out is that there's another rule that's at play that we haven't had to use yet, which is the current rule, which I mentioned all the way back when we were doing the first problem. I said that there's going to be a way to sort of put all these currents together. Notice how I1 and I2 are both going to flow into that point that I made right there, right? We're going to have I1 coming from the left and I2 coming from the right. And you can imagine that we have water rushing at it from two different sides into a point where these two pipes meet, and there's only one place for the pipes to go, just straight down. So the water, I1 and I2, or the current, has to meet and then make I3 going straight down. And this gives us our current relationship, or a junction rule, and that tells us that the sum of the currents into a junction has to be equal to the current out. So that's I1 plus I2 is equal to I3. Okay, now we can go ahead and use our loop rule. This is going to be one equation that we are absolutely going to use. So go ahead and sort of put it up here. We will use this at some point because we need to find the current through resistor 2 and resistor 3, which is I2 and I3. And so, yeah, so now what we just need to do is our loop rule. Now, you can proceed with these loops in any way that you want to. Just remember our rule is that we have to do a complete loop. So you have to start and end where you started. So when we're doing the loop rule, you have to start and end at the same place. So start and end in the same place. That's one rule. And then the other rule is for batteries, I'm going to put EMFs. We add when going, let's see, we'll add voltage when we're going from negative terminal to positive terminal. And we subtract voltage when going from positive terminal to negative terminal. And then for resistors, we subtract voltage when going with the assigned direction or the assumed direction of the current. So as we did previously in the last problem, for instance, when we're going in this direction over resistor R1, we will subtract the voltage of resistor R1, which is an IR, I1, R1 in this case. If we were to go the other direction, we're going against our assumed direction for the current, then we would actually have to add the voltage back in. We'd have to add back in I1, R1, just because we're going against the direction of the current. And just to review our battery rule one more time, when I'm going from the negative terminal to positive terminal of a battery, like I've indicated right here over epsilon1, I will add voltage in. If I find myself traveling along a loop where I go from the positive terminal to the negative terminal, I have to subtract the voltage out. So it's just, I have to be consistent with the directions that I'm traveling, right? That's the important thing. As long as I'm consistent with the directions I'm traveling, and as long as I start and end in the same place, my loops will be valid, and the equations that I come up with will sum to be equal to 0. So the way that I typically, if you'd like to have a way to approach this every single time, my recommendation is going to be to start and end my loops at whichever point I use to set up the junction rule. So I've already used this point to set up my I1 plus I2 is equal to I3. And I'm also going to use that as a starting place for my two loops. And one loop is going to be this, which I will call loop 1. And the other loop is going to do this. And I'm going to call that loop 2. And it's going to give me two different equations. And I'm going to I'm going to write down both of those equations, set them equal to 0, and then I'll have a system of three equations. And I can solve a system of three equations using algebra skills. Okay, so just to label those loops on my circuit, we're going to call this one loop 1. And we're going to call this one loop 2. And let's go ahead and write down our equations. So we're going to sum the voltages around loop 1. And it's going to be ultimately equal to 0. So I go down through R3. I'm going with the current I3. So I'm subtracting the voltage over R3, which is I3 R3. And then I'm going to add epsilon 1. And then again, I go with the current through R1. So I subtract that as well. So just to do all those again, I'm going down through R3 in the direction of I3. So I have minus I3 R3. Nothing happens on the where's my laser pointer? Nothing happens down here. And then I go up through epsilon 1 from the negative terminal to positive terminal. If I go negative terminal to positive terminal, then I have to add in that epsilon 1. And then I continue along and I go with the current I1 through R1. So I have to subtract again the IR through that guy, which is minus I1 R1. And then this whole thing has to be equal to 0 because I end up back where I started, and thus that's loop 1. And then the last thing is to do loop 2. So sum the voltages around loop 2. We're going to get a very similar equation. Again, we're going to go down through R3 with the direction of current I3. So that is a subtraction of that voltage. We have minus I3 R3. Trying to make that a little cleaner. So minus I3 R3. We continue traveling down to the right. There's nothing on the bottom part of this loop. Then we're going to go negative to positive through epsilon 2. So we're going to add in epsilon 2. And then continue to travel. Now we're going to go with the current I2 through resistor 2 and end up back where we started. So since we're going with I2, we have to subtract I2 R2. And then since we end up back where we started, we can set this whole thing equal to 0. All right, so there are two equations, and now you can sort of solve them however you'd like. We have a ready-made way of substituting out I3 for I1 and I2 up here. And then we'd have, if you were to do that substitution in these two equations, then you'd have two equations where your unknowns are just I1 and I2. We know the resistances. They're all the same, actually, so it's just a constant R. And we also know the epsilons. They're called E1 and E2, but that's epsilon 1 and epsilon 2. So you can go ahead and plug those in and solve, and I'll leave the algebra up to you. But the important thing here is my loop rule and my junction rule. So the junction rule gives me my first equation, and then my loop rule will generate two more equations, and then I can proceed with the algebra. Okay, so we're going to use that loop rule for other problems that aren't just the two battery problems like this. And problem number 4 is an example of one where we're going to use our loop rule kind of to our advantage here. So we have kind of a complicated problem. In this problem, we only have one battery, which is nice. But the resistor arrangement is pretty tricky. So we have kind of this diamond shape. Okay, so this right here is already enough. We have these resistors all have names, 1 and 2, and 1 and 2. We have kind of symmetry, and you could say here that you could have two different sides that are both in parallel, right? So you could say right now that this side is in parallel to this side, and also they're symmetric. So you could sort of just multiply your equations by 2 and sort of proceed that way. They should have the same voltage dropped across all of them. The tricky part, though, is that we also have this horizontal branch. And there's a resistor there called resistor 3. And so what's going to happen there is that if there's a difference in voltage between these 2 points, then current is going to flow over resistor 3, either to the left or the right. We don't necessarily know which direction it's going to go. But we have to pick one and then sort of solve the problem from there. Okay, so the one thing that I did mention is that we have symmetry, and so that allows us to say that we will have the same current flowing over both this resistor 1 and this resistor 1. So we can go ahead and call both of those I1. And the same argument will give us the same current over these resistor 2s. So we can go ahead and call both of those I2. And then we simply need to pick a direction for I3 that flows over resistor 3. If we ultimately get a negative out, it tells us that we just picked the wrong direction. So I'm going to go ahead and say that we'll just pick to the left, okay? And we'll call this I3. And cool. All right, and then we have names for a bunch of different points here. This one is A, B, C, and D. And they just ask us to find the voltage difference between 2 different points for a bunch of them, right? So VA minus VB is just going to be, if I'm going from A to B, that's just however much voltage I drop over resistor 1. So ultimately, my first step is going to be to find all these currents. Once I find all the currents, then I can go ahead and find all of these potential differences. And I don't think any of them, yeah, it's all just a difference over one circuit, over one resistor each. So, okay. The only thing is I think part A and part C, in A we're going over A to B, and in part C we're going C to D. So in those two cases, since we have the same resistance, R1, and the same current, I1, those answers are going to be the same. But anyway, our goal, again, just as we did in the last problem, step 1 is to find these currents. So the first thing is we do our junction rule. So pick a junction where you have currents flowing in, currents flowing out. You could do either this one or this one. They'll give you the same equation. But to the right, we have I1 coming in, and then it's forking off into I3 and I2, right? So I1 comes into point B, and then I2 and I3 flow out. So to turn that into a mathematical equation, that's just telling us that I1 is equal to I2 plus I3. Okay, and we have an EMF here on the left-hand side, and we know that EMF is going to be dropped over whatever path we happen to take through the circuit. So to turn this into a loop rule, you have plus this EMF minus, say, this resistor, this voltage over this resistor minus this voltage over this resistor, and then you get back to the beginning. So that's one equation that you could have. You could go over the same side, the other side, right? So you have this EMF is dropped over this resistor and then this resistor. That's still going to give you the same equation, right? But let's go ahead and write that equation down. So that loop would tell us that the total EMF of the battery minus I1 R1. I'm doing just this side. It'll be the same regardless of which side you go through. Minus I1 R1 and then minus I2 R2 is equal to 0. And I know R1 or R2. Cool. And so I just have to find one more path. As I mentioned, if I do this path, I'm going to generate the same equation. So I want to pick a path that takes me through resistor 3. And I would like to not go backwards. I'd like to go with the direction of the current. So I'm going to do this. I'm going to go to the left through resistor 3 and then do the other resistor 1. So that loop will give me that I have epsilon minus I1 R1. So I have minus I1 R1 and then minus I3 R3 and then minus another I1 R1. So minus I3 R3 and then minus another I1 R1. And this is all, oops, equal to 0. Okay, so you'll essentially have two I1R1 terms there, which can be combined together. And then again, we can substitute out I1 in each of these equations for I2 plus I3. We'll solve for our currents. And then once you solve for the current, in order to actually give your answers will just be the voltages that are dropped over the corresponding resistors. So once I find I1, I2, I3, I have to go back to the puzzle and say, okay, for part A, we want VA minus VB. What does that mean? That just means what voltage is dropped over resistor 1. So you just do I1R1, where you will have found I1. And then, for B to C is right here. So you'll do I3, R3, and so on. Okay, so leave that algebra and that final solution, the end solution there up to you. But just as a reminder, your voltage, excuse me, for all four of those parts will just be some I times some R. All right, let's go to problem number 5, the mystery box problem. Again, these problems have been the same for, I don't know, a decade or so. So this problem, this problem we have a circuit again. Now we don't have our battery. We just have 2 points A and B, and we're just assuming that there's sort of a battery connected over those terminals. All right, but what is our setup here? We have resistor R1, and then we have a split. This is resistor 1, and we have resistor 2, and then we have mystery box. That's our top split, and then we have resistor 3, and they connect, and there's point B. So we go from A to B, and they give us the voltage from A to B. That's essentially saying you plug a battery into A and B, and that battery has a voltage of 77 volts, right? And what else do they give us? They give us resistors 1, 2, and 3, and they give us the current through resistor 3. So this is the I that is given in the problem. And since I know resistor 3 and I know that current, I can solve for the voltage on this side. It'll be I times R3. Why does that voltage matter to me? Well, notice that I have a parallel split here. So this side is in parallel to this side. And remember, a rule for a parallel split is that the voltage has to be the same on each side. Another way of looking at this is I could do a loop rule. And when I do a loop rule, I would get that parallel split out. Okay, so we'll go ahead and call this voltage 3. And once I know voltage 3, I know that has to be equal to the sum of these two voltages up here. Now, I don't know anything about this mystery box. In fact, they're asking me, is it adding or subtracting energy, right? So they're even saying, like, we don't even know if this is a resistor or a battery. We don't know anything about it. But what I do know is that the voltage that is dropped over 3 has to be equal to the voltage that is dropped over 2 plus or minus the voltage of the box. So to make sure that I keep this straight and that I keep my sign rules correct, let's go ahead and use the correct signage on each of them. So I'm going to have some voltage here that's going to be a positive value, but I'm going to say that that is a negative V3, because you're going to get something like 100 volts out, right, for V3 when you do the current times the resistance. But we're going to say that that's negative because that is voltage that is subtracted by the resistor. That is to be equal to the voltage that is dropped by that is dropped over resistor 2, so it'll be minus V2. And then we'll write plus V box. So the reason why I put the negative signs on these resistor voltages is so that when I solve this equation eventually, I can't do it right away, but this is so that when I solve this equation eventually, if I get a V box that is negative, that tells me that the box is a resistor. And if I get a V box that is positive, that tells me that the box is a battery of some sort. Okay, so as I mentioned, we know V3. V2 is going to be some current times R2, but I do not know that current right out the top. So I do need to investigate V2 a little bit more. So let's go back to our circuit. Now, I have a current that was given, which we'll go ahead and say, we're going to call that current I3. This is the current that's given. And I know that there's going to be some current through resistor 2, which we'll call I2. And I know that I could set up some sort of current rule here with the current through I1, or the current through resistor 1. So looking at all these currents, we have I1 that flows in, and then I2 and I3 that flow out of that junction. So that will give me an equation I1 is equal to I2 plus I3. And then I also know that I have 77 volts that I gain in going from B to A, and then I could complete a loop, right? In other words, this is a battery, and then do a loop. So all of that together is to say that 77 volts has to be equal to the voltage dropped over resistor 1 plus the voltage dropped over resistor 3. And I know that the voltage over resistor 1 is just going to be that I1 R1. And I know that I've already found my V3 right here. So since I have R1 as well, I can go ahead and solve for I1 as my only unknown here. And now I have I3 given in the problem, plug it in right there, and I have I1. So now I can finally solve for I2 from my junction equation. And that's what I need for resistor 2 here. So then I can go ahead and plug everything in here. I will have found something like, minus 100 volts for V3. That was the very first thing I found. And then I'll have this is equal to the opposite of whatever the I2 is that I get out here times the R2 that's given. And then I'll just solve for V box. If it's positive, then I'm providing energy. If it's negative, then I'm removing energy. And the last thing they're going to do is ask to find a rate at which energy is being added or subtracted. Rate is a power question. Now the rate that energy changes is power. So for a resistor, that's usually I squared R. Since I'll solve for a voltage for the box, I'll just use a sort of adaptation of this, which is I times V. So I'll know the current through the box, right? It's going to be the same I2. And then I'll just plug in the voltage for the box here and multiply it by whatever the I2 is that I had to plug in right there. All right, so that's a little bit of a weird problem as well, because we have sort of the mystery box and we don't exactly know. But again, what are our rules? What are our fundamentals here? We're using our junction equation to set up an equation for the 3 different currents. And then we are using kind of an adapted loop rule. Now we don't have a strict loop, but we're using the fact that we know the voltage between A and B. We're sort of connecting that in our head and saying, okay, that battery, that 77 volts from that battery has to be dropped over any loop that we take through the circuit. And that allows us to set up this equation. This is just another loop equation. And so it's, again, junction rule for the currents, loop rule for the voltages, and then you're solving them accordingly. This is also, again, another loop rule, or a derivative of the loop rule, which is the parallel voltages being equal over a parallel split. All right. Problem number 6. Problem number 6 is an annoying one because we have to do several circuits, 4 in total, with different resistances in each. And we also have 2 batteries in both of them, in all of them, that have internal resistances. So we have an epsilon and we have a little r. So I'm just going to talk about the approach to at least the first 2, where we have to do the parallel series once, and we'll set up the equations at least. So we have one of these circuits is called circuit A, and the other one is called circuit B. So circuit A, we have a little internal resistor of this battery, and then we have an identical one below it. And then both of these are connected to an external resistor, big R. Okay, this is big R, this is little r, and these are epsilon, epsilon. And yeah, our voltage sources are constant. So we know that we're going to have, since these batteries are identical, we know they're going to have the same current flowing through them. So we could say through both of them, we have, say, an I1 that's flowing to the left, because it's probably going to flow in the direction from that would point us from the negative terminal to the positive terminal of the battery. And then they're probably going to flow into this junction, I1 and I1, and it's going to send an I2 out. So my equation, again, I'm doing the junction rule. I have an I1 and I have an I1 flowing in here and an I1 flowing in there, and then an I2 comes out. So that's I1 plus I1 is equal to I2. I1 plus I1, which is just, sorry, I was going to simplify it anyway. 2I1 is equal to I2. All right, so that's a relationship between the currents. And then we want to generate a loop rule. Now we have basically two different loops that are both going to be identical. So I'm going to start from this junction, and I'm just going to do this loop down here. We're going to subtract the current over this resistor because we're going with the direction of I2. And then we're going to subtract the voltage over this resistor, and then we're going to add in the voltage of the battery. So to put that all together, we have minus I2 big R minus I1 little r plus epsilon is equal to 0. And you could rearrange this equation, but we have essentially here two equations, two unknowns, and that will allow us to solve for the currents. And they ask us the current in the external resistor. So in either case, we're asked to find I2 ultimately. The other circuit arrangement that we have is, rather than these two batteries being connected in parallel as they are here, we connect them in series. So this is called circuit B. And I'm going to sort of section this off a little bit. For circuit B, yeah, so we have little internal resistance plugged into a battery. And then, you know, kind of the both same, it's a little ugly, but, and then we have this external resistor, big R. Okay, so we have little r, we have epsilon, epsilon, and then we have this big R. So in this case, we only have one current because we just have one single loop. So it's all just our current I. And we could just start here and just go around the circuit and just add up all the voltages. So we're going to go through our first battery, which has the internal resistance little r. So we have to subtract the voltage of our internal resistance for the first battery, which is I times little r. And then we have to add in the epsilon for that first battery. So that's our first battery. And then we have to do the exact same thing for the second battery. So we have minus another I times little r plus another epsilon. And then we will subtract I times the big resistance, big R, minus I times big R. We set this equal to 0. Now again, in this problem, or in this arrangement rather, we're again going to solve for little I. So little I will be equal to some value. And up here, you'll have I2 is equal to some value. And it'll be some expression for big R. And then they give you a relationship between big R and little r. So for parts A, B, and C, you're going to do big R is equal to 2 times little r. And you'll get one answer for the current. And then for D, E, and F, you're going to use big R is equal to little r over 2. And that'll give you a different answer for the currents in each arrangement. And, excuse me, for ultimately which arrangement provides a greater current. However, the math in the setup is going to be the same. So my recommendation would be to generate just an expression for I2 and for little I. And then you can just plug in the different big R values for each of them. All right. Problem number 7 is an ammeter problem. And so for the ammeter, what we need to know about the ammeter is that it has no resistance. An ammeter just measures current flowing through a point, and it again would have no resistance. So the circuit here looks a little funky, but it's actually not too difficult to tackle. We have one branch, and we have kind of another branch, and then we have our ammeter through the middle. And we would have symmetry here if it weren't for the fact that this resistor right here is just called R1, while all the other ones are just called R. Okay, now what's going to happen is since the ammeter has no resistance, there's going to be a balance between these 2 points, and we're going to have the same current flowing over both of these, which we can go ahead and call, we'll go ahead and call that, let's call it I3, although it's going to be related to the currents in the other ones in a kind of peculiar way. So we'll go ahead and call this one I1, and we'll call this one I2. Okay, so how is this all going to relate? It's not exactly I1 plus I2 is equal to I3, but what's going to happen is I1 and I2 are going to flow into these 2 points, the 2 sides of the ammeter. Some stuff's going to flow out or move across the ammeter, but I1 and I2 are going to come in, and then there will be 2 I3s flowing out. So putting that all together, then we can still generate a junction equation for our currents. It's just going to be that I1 plus, plus I2 is equal to I3 plus I3. In other words, 2 I3s. Okay, and ultimately, if I need to find the current that flows over the ammeter, I just need to find the difference between, say, I2 and I3, or I1 and I3. They should be the same difference. And the reason why that will be equal to the difference that flows over is because let's say that 4 amps flows in for I2. If 4 flows in and then 3 flows out, how much flowed over the amp meter? 4 in and then 3 kept going down. That means the other 1 went across. So that's why you just subtract them at the end to find your answer. Now, the way that I find the actual values for the currents is, again, I just need to know that I have an epsilon here, and then I can just do my loop rules. So I would just do 2 loops, actually. I do this loop right here. That would be, I'm going to call that loop 1. And then this loop around the outside will be loop 2. And I think that that'll be enough to generate, because I have 3 unknowns here, so I just need 3 equations total. So yeah, so this first loop, I have epsilon minus I1R1 minus I3R. So that's epsilon minus I1R1 minus I3R has to be equal to 0. And then my other loop is around the outside. So I have epsilon minus I2R minus I3R. Epsilon minus I2R minus I3R. That will also be equal to 0. All right, so there we go. I have 1, 2, 3 equations. I have my 3 unknowns. I have, R1 is given in terms of big R. So that's enough there to solve. And I do not know epsilon, but ultimately I will give my answer for the current in terms of epsilon over R. All right. And the last problem here is an RC circuit. And unfortunately, the only problem that we have is sort of a more complex RC circuit. So what I'm going to do is I'm going to take a step back and talk a little bit about RC circuits in general, and then we'll talk about this problem itself. I think we're doing all right in time. So an RC circuit in general, here's the way that works. You have a battery that's connected to a resistor and a capacitor. This is not the one from the homework. I'm just sort of making up a new one here. And yeah, I'll go ahead and call this epsilon for the battery. Okay, so what happens is usually you have a switch and you close the switch, right? So we close our switch. What's going to happen is if I did not have a resistor here, when I close my switch, what would happen is charge would just store up on the plates of the capacitor instantaneously, and that would be it. That would be the whole problem. Since there's a resistor there, we know that resistors resist the flow of electricity, and so it's actually going to take a little bit of time for the charge to build up on the capacitor. And so what we actually have is that the charge on the capacitor can be written as a function of time, and that function is going to depend on the resistor according to Q, what we'll call QM, Q max, times 1 minus e to the negative t over RC. So this is the charge on the capacitor as a function of the resistor, the resistance and the capacitance, and of course time. It takes some time for the capacitor to charge up because the resistor is there. You can also, of course, relate this back to the voltage on the capacitor. So the voltage on your capacitor as a function of time is going to be equal to epsilon, whatever the voltage is of the battery, times the same thing inside 1 minus e to the negative t over RC. Okay, so this is for a charging RC circuit. You can also discharge a capacitor. In this case, what you would have is you'd have, say, a capacitor that is already charged up, that has some positive charge and negative charge, and you're going to plug that capacitor into a resistor. Now what's going to happen is the charge is going to want to leak off of the capacitor, but the resistor is again going to resist the flowing current that is produced by that capacitor. And so now you have a slow discharge of the capacitor. So you have a Q of t that is equal to whatever the initial charge is times e to the minus t over RC. It's just an exponential decay. And I'm not even going to write this voltage because there is no epsilon for this one, but you'd have some initial voltage as well that's stored across it. Well, I'll go ahead and write it. The voltage over the capacitor as a function of t would be, say, a voltage initial times e to the minus t over RC. Okay, so in your notes, what do you want to write? You want to write that these equations are for charging RC circuits, and you want to write that these equations down here are for discharging RC circuits. And we'll go ahead and take a look now at the actual homework problem, which is a little bit more advanced. So in the homework problem, we have a switch here, and then we have resistor, another resistor. Okay, this kind of looks like a resistor circuit, right? This is R2, this one is R1, but we also have a capacitor through the top. And so it's kind of like our capacitor and our resistor R2 are connected in parallel, roughly. And so, yeah, so what you're going to do is you're going to close the switch. And when you close the switch for a very long time, what's going to happen is the capacitor will charge up. And once the capacitor charges up, you have essentially all of the charge of the battery stored up on the capacitor. The voltage across R2 rather, which is, just one second, let me make sure that I get this right. Yeah, okay. So after a very long time, you would have a voltage across the capacitor, which we'll call our, that's a current direction, but we'll go ahead and say that trying to think of what symbol to use for the voltage of the capacitor. We'll say that our voltage over our capacitor, which is going to be equal to our V naught in our discharging equation that I wrote on the last page, right? This is the equation that we ultimately want to use because we're going to discharge. That voltage has to be equal to the voltage over resistor 2. And that's because we are in parallel, as I mentioned. And we know that our total voltage over this whole thing has to be equal to, we can use our loop rule, right? So we have, this is an epsilon. That allows us to write the equation that epsilon is equal to R2 times the current. So we'll call that I times R2 plus I times R1. And this will allow us to solve for a current equal to epsilon over R1 plus R2. And since this will be the current over R2, I can use it to find the voltage over R2 as well. So voltage over R2 will be equal to the current times R2, where this right here is our current. Okay, so all of that allows us to write down the initial voltage over the capacitor. Now we can go ahead and open the switch. And when we open the switch, what's going to happen is the charge that is stored up, it would actually be this charge. This charge, once I open up the switch, it's like I've removed all of this. Whoops, I want to keep R2, but it's like I've removed all of this stuff from the circuit because I opened a switch. It's no longer connected. So my circuit is now just this loop, and the capacitor wants to discharge through my resistor R2. So my voltage of the capacitor as a function of time will be equal to V naught, which is actually I times R2, which is actually R2 times epsilon on R1 plus R2, times e to the negative t over RC. And they give us RC. Keep in mind that R here is R2. So it'll be R2 times the capacitance. The time on top is, they're going to give us an explicit time of a couple milliseconds. And that'll allow us to find the voltage over the capacitor. And yeah, and then once we have that voltage over the capacitor, that will tell us the voltage as well that is over the resistor. And they ask us inevitably to find the current of the resistor. So once you find this voltage, then you would set this equal to, again, voltage 2 is equal to I2, which we're solving for, times resistor 2. Okay. So this one is a little bit of a complex sort of example of an RC circuit. And we are strictly discharging here. The charging process is a little strange because we have the capacitor and R2 in parallel initially. But ultimately, remember, we want to discharge down to 0. The time that's given is going to be the time to half of the maximum voltage, and you'll, or not, it won't be quite the time to half the max, but yeah, anyway, so you'll find the voltage, and then the voltage has to be the same across the two because they are connected in parallel here. And so you set the voltage over the capacitor equal to the voltage over the resistor again, and then set that equal to I2 R2 and solve for the current over resistor 2. All right, so that's at an hour. I'm going to go ahead and leave that there. If you have any questions, feel free to shoot me a message on Canvas. And if not, have a good weekend, and good luck on the exam next week as well. I'll talk to you later.